Welcome to this lesson on Euler's method for approximating solutions to differential equations. Today, we'll be solving an initial value problem step by step using Euler's method with different numbers of steps. Let's look at our initial value problem. We have dx over dt equals 1 plus t times sine of tx, with the initial condition x of 0 equals 0. We want to find the value of x at time t equals 1. Euler's method is a numerical technique for approximating solutions to differential equations. The idea is to use small steps, each of size h, to march forward from our initial condition. At each step, we use the derivative to predict the change in x, and then update x accordingly. Let's visualize what Euler's method is doing. We start at the initial point, then take small steps in the direction of the derivative. The smaller our step size h, the more accurate our approximation should be. We'll try different numbers of steps, 1, 2, 4, and 8, which correspond to step sizes of 1, 0.5, 0.25, and 0.125. Let's start with n equals 1, which means we'll take just one step of size h equals 1. We begin at t0 equals 0 and x0 equals 0. The derivative at this point, which we'll call f0, is 1 plus t0 times sine of t0 times x0. Since t0 and x0 are both 0, this simplifies to just 1. Now we can calculate x1 as x0 plus h times f0, which gives us 0 plus 1 times 1, which equals 1. So our approximation at t equals 1 is x approximately equals 1. Next, let's try n equals 2, which means two steps of size h equals 0.5 each. Again, we start at t0 equals 0 and x0 equals 0. The derivative f0 is still 1. For the first step, we calculate x1 as x0 plus h times f0, which gives us 0 plus 0.5 times 1, which equals 0.5. So at t1 equals 0.5, we have x1 equals 0.5. For the second step, we calculate the derivative at t1 equals 0.5 and x1 equals 0.5. This gives us f1 equals 1 plus 0.5 times sine of 0.5 times 0.5, which is 1 plus 0.5 times sine of 0.25. Sine of 0.25 is approximately 0.2474. So f1 is approximately 1.1237. Now we calculate x2 as x1 plus h times f1, which gives us 0.5 plus 0.5 times 1.1237, which equals approximately 1.06185. So our approximation at t equals 1 with n equals 2 is x approximately equals 1.06185. Now, let's try n equals 4 with step size h equals 0.25. Following the same procedure, but with 4 smaller steps, we would get the intermediate values. t0 equals 0, x0 equals 0, t1 equals 0.25, x1 approximately equals 0.25, t2 equals 0.5. x2 approximately equals 0.53, t3 equals 0.75, x3 approximately equals 0.83, and finally t4 equals 1, x4 approximately equals 1.13920. So our approximation at t equals 1 with n equals 4 is x approximately equals 1.13920. Finally, let's try n equals 8 with step size h equals 0.125. With 8 even smaller steps, the computation becomes more tedious, but following the same pattern, we would arrive at an approximation of x of 1 approximately equals 1.19157. Let's summarize our approximations at t equals 1. With n equals 1 step, we got x approximately equals 1.00000. With n equals 2 steps, we got x approximately equals 1.06185. With n equals 4 steps, we got x approximately equals 1.13920. With n equals 8 steps, we got x approximately equals 1.19157. Notice that as we increase the number of steps n, our approximation gets more accurate. The values are growing, suggesting that the true value of x at t equals 1 is greater than 1.19157. If we wanted an even more accurate approximation, we could use even more steps like n equals 16 or higher. Euler's method is a first-order numerical method, meaning its error is proportional to the step size. As we decrease the step size by half, we roughly have the error in our approximation. This is why we see our approximations getting closer to the true value as we increase n. The general formula for the error in Euler's method is proportional to h, meaning if we double the number of steps, having h, we approximately have the error. In conclusion, Euler's method provides a simple yet powerful way to approximate solutions to differential equations. While more advanced methods like Runge-Kutta offer better accuracy, Euler's method gives us a clear understanding of the fundamental concept of numerical integration of differential equations. Thank you for watching.